Okay. Hi, everyone. Welcome back to part 2 of lecture 13. And now we're going to talk about the vertex cover problem. All right. So here's the problem that we're going to solve right now. So the setup here is our input is a graph again, right? And what we want to output is the minimum number of vertices that touch all the edges of the graph. Okay, so we want to output the minimum number of vertices S, such that for each edge we have that S intersects this edge in at least one of its vertices, right? So in picture, what do we want? So let's say that we have this graph here. Let's say that our graph G, and then we have these vertices. Okay, and now what would be what will be a vertex cover here, right? So one vertex cover that we can take is this guy, and then we can take this guy, and then we can take this guy, right? So this is a vertex cover. And what else? Well, what is another vertex cover, right? So we can take another vertex cover to be, okay, let's take this guy and this guy, right? You can also see that both of them are vertex covers. Does that make sense? Because both of them are covering every edge of the graph, yeah? So if you look at any edge will either touch the set. Let me just do the examples like more. Let me kind of number the vertices, right? So suppose that I have here, like, let me number maybe 1, 2, 3, 4, 5, 6. And we saw that the first cover was S equals to 1, 2, 3 is a cover. And we also have S equals to 1, 5 these are covers, right? Because if you look at 1, 2, 3, well, any edge is between someone on the left side and the right side, so this is easy to see. Then 1 and 5, let's see 1 and 5. What happens here? 1 and 5, right? Now note that any edge that goes out of 1, okay, is covering the first 3 edges, right? And the ones from 5 is covering the other 3 edges, right? Like, so okay, so both are covers, and S is the minimum cover, right? So this the second one, so let's say S1 and S2. S2 is our minimum cover. Is that clear so far? Okay, so now, and so this is the unweighted version that I just showed to you, but we can also have a weighted version that, we associate to each vertex V a certain cost. Okay, so there's a cost to adding that set to that vertex to your set, right? Because some nodes may be more important than others. Okay, so all right, so what do we do to solve the vertex cover problem, right? So here what we do is we set up the vertex cover as an integral linear program. Okay, so what do? We minimize the cost. So here's the sum of the cost of adding u and times xu. And remember, xu here will be what? Xu is encoding like 1 if add like u to s and 0 otherwise, right? So if we have these integral variables, right, they're exactly encoding the set s. So what are we doing? We want to minimize the cost, like the total cost of set S, subject to what? Well, okay, so this is capturing inclusion in S, right? So inclusion in S or not. But what are our constraints? Well, these constraints here is saying what? They're capturing exactly the fact that S has to cover every edge, right? That it intersects every edge in at least one of its vertices. Does that make sense? So this is the vertex cover as an integer linear program. Okay. And all right. So for the unweighted case, so let's try to solve this, the vertex cover problem in the unweighted case, right? So here, if we had unweighted case, we just list the edges E in any order, and let's say that the set S is empty. Okay, so here's a very simple two approximation, okay, which will not involve any linear program at all. So, all right, now for each edge UV, what happens here? Well, okay, so we list the edges in any order, right? And now we start going through the edges, okay, in this linear fashion. So you list them and then you go through the first, second, and so on. Now for each edge, what we're going to say is that look at S intersection UV. So if S does not intersect the edge UV, then let's just add S, like to S, the set, let's just add both vertices, okay? So we're adding both vertices. Both vertices to S, okay? Does that make sense? And then we just keep going. And then in the end, we return S, okay? So, all right, let's just prove that this algorithm, first of all, it outputs us a vertex cover, right? So by construction, S is a vertex cover because after each iteration, if I didn't intersect that edge, then by the end of that iteration, S will intersect the edge. Does that make sense? So if before seeing U, like before seeing UV, we had that S intersect UV was empty, then after seeing UV, we know that S intersect UV is non-empty, right? Because after seeing UV, we will, if the intersection was empty, we will add both vertices, right? So at the end, this is making sure that we have a vertex cover. All right. And now, why does this give us a two approximation? Well, in the unweighted case, right? So if we added elements to S k times, right? So if we added k times, then we know that the size of S is equal to 2k. And why is it equal to 2k? Because every time we add S to S, we add to the set S, we add exactly two vertices, which were not there before, right? So two new vertices. So if I added elements to S k times, the size of S is 2k, and G, the graph, has a matching of size k, right? Because we just proved these vertices, they must be a matching. But now, if a graph has a matching of size k, then the optimum vertex cover is at least k. And why is that? Well, let's look for a matching. So suppose that we have a matching in the graph. Now look at this matching, right? Suppose that our graph was just a matching. Now, how do we prove that the vertex cover here is at least 4? Well, it turns out that if you pick any vertex cover, if I don't pick any of these two, then I know I'm not a vertex cover, right? So a vertex cover has to pick one vertex from here, must pick a vertex from here, must pick a vertex from here, must pick a vertex from here, must pick, right? Like vertex cover must pick vertex from the matching, right? Like vertex from each edge of the matching. Does that make sense? So here we already know that this algorithm gives us a two approximation because we proved that if we added the elements to the S k times, the size of S is 2k, and the minimum vertex cover has to have size at least k, right? So this is a two approximation. And then you may say, okay, well, Rafael, well, why can't we just modify this algorithm a little bit and we obtain an algorithm for the weighted case? Well, okay, so okay, we get to approximation, but here, what can go wrong with this algorithm? Okay, if we apply this to the weighted case, well, here's an example. Suppose that we have like a gigantic guy and this has weight 100 and this is connected to guys of weight 1 like this, right? So this is our graph G. And let's say here, like this vertex is A, well, let's say this vertex A, B, C, D, E. Well, in the vertex cover case, our algorithm, well, let's say that we line them up in alphabetical order, right? So we pick A, B, A, C, A, E, A, D. Our algorithm will pick S will be equal to A, B. But what is the cost of S? The cost of S is exactly 101. What is the optimum here? Well, the optimum would have to be S equals to B, C, D, E. What is the cost of this optimum? Let's say S star is equal to 4. Does that make sense? So, and then you can say, okay, well, but that's because we're picking 2 vertices, like both vertices of the edge. What if we only pick the lowest weight vertex when we see one? Well, then, okay, it's very easy also to modify so that things go bad, right? So let's say that we have 70, and then here we have 50, then here we have 50, then here we have 50, then here we have 50. And then what happens? Well, again, we have A, B, C, D, E. If we only pick the lowest weight, our set S would have been what? B, C, D, E. But what is the optimum in this case? In this case, the optimum here would just have to be pick A and B. Or actually, here vertex coverage is picking A. Sorry, just pick A. Does that make sense? So if you always pick the lowest weight, you could be missing exactly the vertex cover. Yeah. So the vertex cover is a little more complicated here. And now you can see, now let's see how to use the LP relaxation to solve the vertex cover problem, right? So here we have our integer linear program that we already set up before, right? And to solve the weighted case, now we saw that we need a different algorithm, right? The greedy algorithm won't cut it. So, all right, so this is the integer linear program. And then we're going to drop the integrality constraints. And remember, as we saw in the previous part, this constraint here gets just replaced by being between 0 and 1, right? And now we have the linear program. And what do we do? Well, let's just solve the LP. So let's just get an optimal solution, right? Because we're always assuming in this course that we can solve LPs efficient if they have a small description. And clearly this is a small description, is a polynomial size description. So let's get an optimal solution Z for the linear program, okay? Where Z here is just a vector, right? Like each of these ZU is in 0, 1, right? Like is between 0 and 1. All right, but this is an optimal solution. Now, what do we do with this optimal solution? Well, okay, here's how we're going to round the LP, okay? So each of these ZIs is between 0 and 1, so we're just going to round ZV to the nearest integer, right? So what do we mean? If ZV is, so ZV, okay, so the rounding of ZV will be what? ZV will go to 1 if ZV was greater or equal to 1/2, and it'll go to 0 otherwise. That's what we're doing, right? Because the ZV is their feasible solution, and we're just sending them to, okay, to an optimal solution, right? All right. So, okay. So now we got the optimal solution, and we did this rounding, right? So now we're going to say, like, we're going to construct the rounded solution is YV. And YV will be 1 if ZV is greater or equal to half, and YV will be 0 if ZV is less than half. Now, the first question that you must be asking is, wait, is Y, this new vector Y, a feasible solution? Okay, and what is the answer, right? Well, okay, so Y is definitely an integral cover, right? So Y is the integral by construction, but each edge is covered, right? So why is this a covering? Because given UV in E, at least one of ZU and ZV is greater or equal to half, because we know that ZU plus ZV must be greater or equal to 1, which implies that one of ZU or ZV is greater or equal to half, correct? Because if both of them were less than half, the sum would be less than 1. Okay, so in particular, so in particular, which implies that one of YU, YV is greater or equal to 1, which implies that YV is a cover, right? Okay, so we know that Y is a feasible solution because Y is a cover. And okay, so now what is the cost of Y, right? So how do we measure like the cost of Y here? Well, here's the thing. We know that, yeah, let's just run through this inequality. So we know that each YI, right? So, all right, so we know that each, okay, so let's go here. So we have the sum of CU, YU, U in V, correct? And now here's the thing, right? What do we know about YU, right? So we know that YU is less than or equal than 2 times ZU. How do we know this? And why do we know this? How do we prove? Well, if YV is equal to 1, implies that if and only if ZV is greater or equal to a half, which is if and only if like 2ZV greater or equal to 1, which is equal to YV. So that proves in this case. And if YV is equal to 0, this is if and only if ZV is between like 0 less than or equal to ZV less than or equal to a half, which implies that YV, which is equal to 0, is less than or equal than 2 times ZV. So always we know that this inequality happens, which in particular implies that the sum of CU times YU is less than or equal than CU times 2 times ZU because of the inequality, right? This is greater or equal than YU. But now we know that this guy here is equal to sum, like 2 times sum of CU ZU. But remember, this part here in red is the optimum of the linear program by definition. But the optimum of the linear program is less than or equal than the optimum of the integral linear program. And therefore, we get the second inequality. Okay. So what we showed is that this rounding that we just did, okay, we solved the LP and we just round to the nearest integer, and the solution that we got, the cover that we got, is no worse than twice the optimum of the linear program. Does that make sense? So this is the vertex cover solution, and we still get a 2 approximation, but now for the weighted case. Does that make sense? So here, it's really impressive that the LP is just dealing with all the cases that we could have been dealing with. They're just being dealt with the LP to get the same approximation that we got for the unweighted case. Does that make sense? Okay, if so, then let's go to the third part of the lecture.